All right, now we're going to introduce the concept of a congruency, and the mod is very important for this. Okay, so we say if a and b are integer and m is a positive integer, then a is congruent to b modulo m if m divides a minus b. Right, so this is the notation for a congruency. So a is like the triple lines, b mod m. Right? So you say that a is congruent to b modulo m. That's how this reads. Right? What this means is represented by this theorem. Okay, so a is congruent to b modulo m is if a and b, when you divide a by m and you divide b by m, you get the same remainder. Okay, so this theorem represents that. So it says that a is congruent to b mod m if a mod m is the same as b mod m. So right here, a mod m is the same as b mod m. Okay, so there's kind of two different ways to check congruencies. All right, so either this way, that m divides a minus b, or that if a mod m is the same as b mod m. Okay, so basically you say the two numbers are congruent to each other. Congruency often means that they're equal, but not really equal. They're congruent to each other in a certain modulus if you get the same remainder when you divide those numbers by that modulo, by m. All right, so let's look at this example here to demonstrate. So determine whether 17 is congruent to 5 modulo 6. Okay, so let's look at this problem first. Okay, so R17 is 17 congruent to 5 modulo 6. Okay, so again, there's two ways to check it. So the first way to check if this congruency is if I take 17 minus 5, does 6 divide 17 minus 5? Okay, in case that's yes, because 17 minus 5 is 12, and 6 does divide 12. Because you can write 12 as 6 times 2. Right. But the second way to check it is to see if you get the same remainder if you divide these numbers by 6. Right, so if I do 17 mod 6, right, again, this gives you the remainder of the division. So 17 divided by 6 is 2 with a remainder of 5. So I get a remainder of 5. And if I divide 5 mod 6, so if I do 5 divided by 6, I get 0 with a remainder of 5. So same remainder. That means 17 and 5 are congruent to each other in mod 6, in modulo 6. Okay, now let's look at the second problem there. The second problem says, are 24 and 14 congruent modulo 6? And so again, we can do it two ways. First is to check to see if 6 divides the difference between the two. And you can say that that's a no, because 6 does not divide 10. Right? And the second way to check it is to check the remainder of the division. If I do 24 mod 6, and again, you can use a parentheses or not, it doesn't really matter, then the remainder to this is 0. But if I do 10 mod 6, the remainder to that division, 10 divided by 6, you get a remainder of 4. So again, not the same remainder, so they're not 10 and, sorry, that should have been 14. So that's a remainder of 2. Okay, so 14 divided by 6 gives you a remainder of 2. They still don't have the same remainder. So they're not, 24 and 14 are not congruent to each other in mod 6. Okay. All right, let's look at this theorem. Let m be a positive integer. The integers a and b are congruent modulo m if and only if there's an integer such that a equals b plus km. All right. So this is an if and only if proof. So we need to do both ways. Okay. So first we need to prove that if a is congruent to b modulo m, then a equals b plus km. All right, so let's look at this. So if a is congruent to b mod m, then m is going to divide into a minus b. We know that from the definition of what a congruency is. Now if m divides into a minus b, then that means a minus b can be written as m times an integer k. That's by the definition of division. All right, and if we solve for a, we get a equals b plus k times m. Okay, so we got to this conclusion. That's good. All right, now let's go the other way. Okay, so the other way means that I start with if a is b plus km, then we want to show that a is congruent to b mod m. All right. Okay, so a direct proof, but this is basically the reverse steps. So I start with this, and I'm going to subtract b, and I have a minus b equals km. But because a minus b is an integer times m, then that means m divides into a minus b. By the definition of congruency, this means that a is congruent to b mod m. So you show that it works both ways. All right, you can sort of these little theorems, the definitions are building up to the tools that we'll need to do operations in modulo. Okay, so operations in modulo with a kind of certain moduli, looking at remainders, are just very important for computers, for computing, because computers don't do arithmetic the same way we do. The way we sort of do addition, multiplication, division, and exponentiation slows computer down quite a lot. So the computers, people use different algorithms based on this modulo arithmetic that make computer a lot more efficient, make them run a lot faster. So not really so important for small numbers, but when you start working with cryptography, with sort of encoding and encryption, then you're dealing with like big numbers, big primes, and big exponentials, and that slows computers down quite a lot. So you want to have efficient algorithms to do arithmetic. So here's another theorem, and this one has to do with sort of subtract addition and multiplication properties for numbers in modulo. You can see we have m is a positive integer, a is congruent to b modulo m, and c is congruent to d modulo m. And we can show, we're going to prove in this theorem, that the sum works. So if I add the a plus c, that's going to be congruent with b plus d modulo m. And this b plus d is like together. And the product, a times c, is congruent to b times d modulo m. All right, so let's see. So we're going to start with our premises. So a is congruent b mod m, and c is congruent to d mod m. Right. Now from the theorem above, Okay, we know that if A and B are congruent under a modulus, then I can write this equation right here. Okay, so if A is congruent B mod M, then that means that A is going to be equal to B plus Km. All right, and I can write C as D plus Lm. Again, don't use the same integer. All right, now we're going to, if I want to prove the sum, we're going to add these together. Okay, so we have A plus C is B plus D, Km, and Lm. So if I simplify this, B plus D is K plus L times M. Okay, now you can see that this has the same format as these equations right here, because I have a number equals another number plus an integer times M. So by the theorem above, then we can say that A plus C is congruent to B plus D mod M. Like this. Okay. All right, now for the multiplication one. So to prove the multiplication, we basically go back to this. Okay, so the congruency is going to get changed in these equations. And now we're going to multiply them. Okay, so let's multiply this. Okay, so A times C is going to be B plus Km and D plus Lm. I'm going to expand this out. So it's BD plus BLM plus BKM plus KLM squared. Okay? Now we want to rewrite this as AC is equal to BD plus M times an integer, because that's sort of the format that we need to show that they're congruent. Okay, so if I factor out an M, I'm going to get BL plus DK plus KLM. Don't really care what's in here. What we care is that this is an integer. So because all these letters here are integers, the sum product, whatever this is also going to be an integer. All right? So this means because AC equals BD plus M times an integer, that means that AC is congruent to BD mod M. So basically this theorem right here proves sum and product properties of congruencies in mod, okay, mod congruencies. So if A is congruent B mod M and C is congruent to D mod M, then the sum of these are congruent and the products of these are congruent. Okay, so again, some of these properties are useful for the arithmetic that we're going to do in a little while. Okay, so let's use those properties on this example. Okay, so if 7 is congruent to 2 mod 5 and 11 is congruent to 1 mod 5, show these congruencies. Okay, so basically I noticed that 18 is 7 plus 11. So using the addition property, okay, you can see because it's the same mod 5 in all of them, then A plus B would be 7 plus 11 is going to equal to 2 plus 1 mod 5. So 18 is going to equal to 3 mod 5. Okay, so that shows that this congruency works. All right, and for this one, we're going to multiply. So we're going to use the multiplication property. So D Right, so again, if I multiply 7 times 11, they should be congruent to 2 times 1 mod 5. So 77 is congruent to 2 mod 5. Keep forgetting the third bar. There you go, all these should be like triple bars there. Okay, so this is a short example on sort of the use of these equations. All right, here's another theorem that kind of shows how to do mod algebra, basically. And I'm not going to prove this one. I'm going to use it to do the example. So there are a couple of properties. It says if m is a positive integer and a and b are integers, then a plus b mod m is equal to a mod m plus b mod m mod m. Okay? And the product ab mod m is equal to a mod m times b mod m mod m. Okay? So I'm not proving them, we're just using them. So let's see how these are useful here. For part A, I have 177 mod 31 plus 270 mod 31 mod 31. So notice that this is in the format here. So we're basically, it's like sort of matches that side of the equation. Okay, so we can see that we can transform it into this. We can say that this is our A and this is our B. This is going to equal to 177 plus 270 mod 31. Right? So if I add these up, I get 447 mod 31. Okay. And we can do this, right? We can evaluate this because this tells me, give me the remainder of this division. So if I divide 447 by 31, all right, we're going to get, wait a minute, let's see what we get. 447 divided by 31 gives me 14, but there's a remainder. So if I do 447 minus 14 times 31, that gives me a remainder of 13. Okay, so the remainder to that division is 13. Okay, so it sometimes simplifies the process, like if you have big numbers, to kind of use either one form or another, it simplifies the process of working with mod sometimes. All right, so let's look at this one. So B says we have 32 cubed mod m mod 13 squared mod 11. Okay, so this is going to use the multiplication property. All right, so we're going to sort of, we're given the form in like at the left hand side, and we need to use the right hand side to transform it. So because this is cube, I can write this as 32 mod 13 and 32 mod 13 and 32 mod 13. Okay, so basically I'm taking the cube, so it's like I have A, B, C, I have 32 3 times, all right, and this kind of goes in parentheses, but according to the formula, there's another mod 13 at the end, all right, and all this is squared, and then the mod 11 comes at the end, okay? So this is basically, I'm expanding 32 cubed mod 13 into this in order to be able to calculate all these easier. Okay, so 32 mod 13 is, what's the remainder if I divide 32 by 13? So 32 divided by 13 is going to be twice, which gives 26, but then we get a remainder of 6. We get a remainder of 6 from here, 1 from here, 1 from here. All right, mod 13 squared mod 11. All right, so this is 216. mod 13 squared. And I can do this division. So 216 divided by 13. Got to find the remainder of that. So 216 divided by 13 goes 16 times with a remainder of 8. Okay, so we get 8 squared mod 11. So 8 squared is 64. And then we do 64 divided by 11, which gives me 5, with the remainder of 9. Like that. Okay? So basically these formulas will aid in calculations that have to do with mods. Sometimes if you have big numbers, you can split them up. Sometimes you have things split up, you can combine them. All right, so one last thing in this section, more modular arithmetic. Let's grab one last example here. Let's see. Okay, so we have modular arithmetic operations. So we have this like plus, so like plus with the m at the bottom and times with the m at the bottom. This is addition and multiplication in modulo. Okay, so if I have a plus b in modulo m, then I'm adding and then I'm taking the remainder. And same for multiplication. So 7 plus 9, like this. This means that I add 7 and 9 modulo 11, right? So this gives me 16 mod 11, which means what's the remainder when I divide 16 by 11? That's a remainder of 5, right? And for multiplication mod 11, I do 7 times 9 modulo 11, 63 mod 11. So 11 goes into 63 5 times with the remainder of 8. Okay, all right, so let's end the section here. And this is preliminary stuff, language and operations that will be used in the other sections in this chapter. All right, that's it.